Okay, so now the last lecture of the physical part of the afternoon session. Marc Bocquet from CEREA, École Nationale des Ponts et Chaussées in French. And again, I'm not going to just read the title that everybody can read, artificial intelligence, etc. Thank you.
Thank you very much.
Listening.
Okay, so I'm going to speak about the data assimilation and the use of machine learning in data assimilation, for data assimilation. And I'm only scratched the surface because since data assimilation involves models, applied mathematics, and data, actually there are many ways to use machine learning into, to sneak into one of those topics or all of them. So there are many attempts actually to use machine learning in data assimilation. And I'm just going to illustrate maybe 2 or 3 of those ways to use machine learning into it. So data assimilation, that's something I'm going to introduce what it is, and this is something that we've mentioned already in the talks before. Right, so the main focus will be probably on numerical weather forecasting. So this is the topic of the day anyway, so that's good. And maybe I'd like to justify justify why we're actually using data assimilation in numerical weather forecast, because this is actually a key component of numerical weather forecasting. And the 2 main reasons actually why we are using data assimilation is the first is the fact that the dynamics of numerical weather forecast and of the atmosphere and most of the geofluids actually in the Earth systems is unstable. It's chaotic. So it means that if you start with different initial conditions that are separated by a small, a tiny difference in the fields, you actually diverge quite rapidly. After a few days, you will diverge. The 2 trajectories will diverge eventually. So even though you get a very good picture of what the state of the atmosphere is, this will ultimately diverge from the truth after a few days. So this is the first fundamental reasons why actually there is something very difficult in numerical weather forecasting. And the second reason is model error, and the fact that, and we discussed that this morning, especially Thomas, this morning actually, so talk about how to represent the Navier-Stokes equations on the atmosphere, on the globe. And what was difficult and the dynamical part was actually pretty well understood and pretty well discretized and implemented in the computer, but still there is all this physics part, or all the processes, the subgrid parameterizations that you have to deal with. So there are many physical process, micro-physical process that you have to account for, so that in the end, even at the level of, the level of PDEs, there are some approximations. So not to mention when you go into a computer and discretize those equations. And so there is model error. So this is the second main source of error when you make any numerical weather forecast, at least for the atmosphere. This is the focus of the talk. And right. Okay. So as far as the model are concerned, we talked about that the whole day long. So it's you pretty know much. Many of the things that you need to know about it. And the main change over the past few years was the use of those surrogate AI-based models, which are now much faster, but essentially of the same accuracy of the IFS, which is considered as the best physical forecast model in the world. So you've got those numerical models or AI-based models, if you want, and on the other side you've got the observations. Okay, and you absolutely need those observations precisely to correct and to help improve the initial conditions that you have on the models, because I just mentioned there are these model errors and the fundamental instability of the chaotic dynamical system. So you really need to use those observations to actually correct the trajectory of the models, and this is where data assimilations comes in, because this is the set of applied mathematical methods that are used to combine optimally those data and the output of those models, those forecasts. Okay, so that's data assimilation. And this has been used for the past 50 years in numerical weather forecast, numerical weather prediction. Okay, and initially it was developed for the atmosphere, for the weather, but then it was also used for ocean forecasting and for atmospheric chemistry, for the cryosphere, for a lot of applications, and even beyond the geosciences. And it went actually back. Some of the ideas that came from engineering, actually, or applied mathematics or computer science, actually went through the geoscience and then went to percolate to applied mathematics back. Okay, so my talk, I will go deeper into data assimilation and we'll try to emphasize some of the points that actually I'd like to illustrate later on when I'm going to speak with on AI and how to use AI for data assimilation. And then I'm going to use two illustrations those are only two standpoints and two specific topics about using AI in data assimilation. But there are many, I really want to stress that there are many ways to actually use, and there are many attempts right now to actually use AI in data assimilation. Okay, and so the first one will be going back to the main topic of the day, trying to learn a surrogate model. But the focus here will be on using noisy and sparse observations rather than using this ERA 5 dataset that we mentioned several times today, which is a clean, regular graded dataset. And thanks to Weatherbench, typically this has been popularized to many different groups in the world. So I'm going to really stress how we can actually use data assimilation to learn a surrogate model, but instead of those ERA 5 using sparse and noisy observations only. Okay, this is going to be the first illustration, the first illustration, and the second one will be on actually learning new things on data assimilation thanks to AI. And I'm going to stress that a bit later, more later on. But let's go back to data assimilation and give some more details on data assimilation. So really, it's to set up the scene and what are typically the kind of magnitudes, order of magnitudes of degrees of freedom, and what are the kind of models that we're actually using. Although there's been a lot of illustrations today already. So typically, this is the kind of dynamics that we were using in data assimilation. This is a typical way to model the forecast model. And here, it does not depend on time. I'm choosing an autonomous system here, but actually it should depend on time. But the important thing is that, so X is typically the state of the atmosphere, and P is the set of parameters. So typically, it used to be a set of physical parameters that we could actually learn within data assimilation. But nowadays, it can actually be a statistical model, typically a neural network, so that P is also the set of weight of variances of a neural network. So maybe we're going to have much more parameters here in this P vector. But it could be anything, physical parameter or statistical parameters or hyperparameters for the statistics of uncertainty within the system. So many different possibilities. Okay? And so typically this eta is a kind of a simple way to model error, to take into account the fact that the model is actually erroneous. It is an approximation of the physics, and it's also discretized on a computer. So all those equations are usually discrete when used within the data assimilation context. And so typically those models, and we talked about that today, so we got the typical physical models here. This is the IFS, or the ECMWF forecasting model. And this is the AIFS, which is the artificial intelligence based on GraphCast model of the ECMWF. And now it has diverged from GraphCast, but originally it was from GraphCast. And this is the same forecast that I took a couple of a month ago for a couple of weeks forecast lead time, and this is the difference between the charts that are actually quite small. Okay, but the big thing, it used to be a big thing, is that it's still a big thing, is that the number of degrees of freedom of pixels that you are accounting for and variables that you have to account for it should be 1 billion at each time step. So that's a lot. That's a really big data. It used to be, and it's still a big data problem. Okay, now the observations. This is the second set of ingredients that we need for data assimilation and for correcting the forecast. And so this is the typical, exemplar of equations that we use for the observation for the observations. Is these observation equations? So with the observation operator HK, and now it really depends on times because you can have, we never have the same set of number of observations, and the instruments can come on and off in a numerical world forecast, so it really has to depend on time. And then there is this errors again, which is now comes, it's of course instrumental error for the observations, but it's much more than that, because actually it's also the errors that you make when you model the observation operator, when you discretize it, and above all, it's actually the mismatch between the representation of the states on your grid and the observations which are quite often, but not always, which could be point size, in situ observations, for instance. So they are not embedded within the same scales. So you need some so-called representation error to actually account for the mismatch between the observations and the states. So these are actually accounts for a lot of types of errors that are very important and really typical in the geosciences. Okay, and typically the number of observations that at each time steps you have to assimilate, to ingest into the system is usually much smaller than the number of grid cell that you have. Okay, and also you've seen this picture already. The main thing is perhaps the fact that you've got several millions of observations that you assimilate every typically 3 hours at the global scale, at the synology scale. And the main thing is that it's usually the source of informations of data are quite heterogeneous, and that's one of the key points. Technically speaking, this is really, even formally, that this is a hardship. Okay, so now we need to combine them in using data assimilation. And so the standpoint, very early in data assimilation, the standpoint has been to have a Bayesian view on combining the two sources of information, models and observations. And to make things simpler, the typical kind of standpoint that people have in mind is typically that of a hidden Markov model. So with the states, which is typically hidden, this is what you want to estimate, and the forecast model that connects the time steps, and you've got the observations that you want to assimilate. So that's typically a hidden Markov model, and you want to estimate those states. And one of the fundamental things that I'd like to stress is because the dynamics is chaotic, you really need to have this type of structure in the estimation of the fields. You need to really do sequential data assimilation in time, because the dynamics is fundamentally unstable. So, and because observations are coming, typically every 3 hours or 6 hours, so you need to update regularly on a regular basis. You need to update the state of the system. So typically and fundamentally, those algorithms that you need to design for data assimilation are actually sequential in time. So typically, this is always the same structure. You've got observations coming in and model forecast, and you combine them within something called the analysis. This is where we just carry out the Bayesian analysis or computing the conditional PDF and take an estimator out of it to make the new forecast. And then, going to the next step in time and using, again, new observations, fresh observations, and combining them once again, and so on and so forth. So really, they must be sequential in time. And so the typical application is for, this is present time, and this is, of course, for forecasting. Then you have to use the model. You don't have any new observations. And this is for typically filtering, estimate the state of the system at the present time, but also for smoothing, going back in time, and use all those observations that are considered as future for those states back in time, so that you can actually have a more accurate estimate of the state of the system in the past. And this is typically what is done in the reanalysis, and this is typically how the ERA 5 dataset has been produced. So using the IFS, using observations, using data assimilation, but in a smoothing manner, using a smoothing algorithm to actually improve on the accuracy of the output. And this is how the ERA 5 has been built. Okay, so the history of the mathematical methods of data assimilation. So typically, it was really what was called the objective analysis, like 50 years ago or 70 years ago. So inspired by the very intuitive way of people were doing to carry out the analysis at the time. But then there were a very simple method, like so typically, best linear estimator, which was called the 3D var. Still, it was a variational method. And then around 2000, actually, the 4D-VAR, which is optimal control. So carry out a variational analysis within a data assimilation window over typically 12 hours in numerical weather forecast, but it could be a longer one if you need to. So this was the advent of 4D-VAR, and it really helped in numerical weather forecast because it was not only was it a very good method for accounting for nonlinearity, but it was also a way to account for the heterogeneity of the data, which was a very, very good thing. And again, I mean, it was using a joint model. I mean, and the advent of machine learning, I mean, was a great help in geosciences because of the fact that we've got now differentiable, more easily differentiable model. And this is what actually they did at the ECMWF and later on at Météo they actually built their own joint of the model so that they could carry out variational 4D-VAR, I mean, variational in time analysis. And this was, one of the first use of backpropagation in this context. But there's been also a set of methods that were inspired by the Kalman filter, and they are called the ensemble Kalman filter. So the Kalman filter is meant to be used on small dimensional systems, and here we've got billions of variables in the numerical weather forecast system. So actually, we need something called an ensemble Kalman filter, which is like a Kalman filter, but meant for the high-dimensional system. And it has some advantage that I will explain compared to the 4D-VAR. And the 4D-VAR has advantage over the ENKF, the ensemble Kalman filter, and I will tell you about them later on. And they've been, I mean, like 10 years ago, they've been combined together to get the best of both worlds. And most of the methods in the numerical weather centers are now using those combined methods for numerical weather forecast that you have every day, like at Météo France or ECMWF. Okay, so I just want to stress, and this is, I want to stress the fact that so there are those two sorts of methods, and the first one is, so typically this is 4D-VAR, and it handles the nonlinearity within a system like optimal control. It handles the nonlinearity of the model very well, so that's the big strength of it. But the other set of methods, the ensemble Kalman filter, actually has an ensemble. Okay, typically like we saw with GenCast. It has an ensemble so that actually it can have an estimate of the errors that the system make when you make the forecast. Okay, and when you carry out the analysis, you get an estimate from the ensemble. You can make an empirical estimate, a Monte Carlo estimate of the uncertainty that you have on the estimation. And this is typically something that you cannot do explicitly with 4D-VAR or the basic version of 4D-VAR. Okay, so that's a big difference with 4D-VAR. And when you play with mathematical models, low-order models, but which still are reminiscent of what's happening for big models, you see that actually the data assimilation window of 4D-VAR is not too big. The ensemble Kalman filter actually is much more accurate than 4D-VAR, and that's because of the way the ensemble Kalman filter handles those errors of the day and estimate the state in the system. And that's really, this is something extremely important in numerical weather forecast, and it has been so over the past 20 years. People are using, even though the centers using 4D-VAR are actually using an ensemble because they need this estimate of the statistics of the errors. Otherwise, you are not as accurate as you should be. Okay, and the outcome of all of this is because of more observations, especially with satellite observations, because of a higher resolution model, and especially because of the way you combine them with data assimilation. It's been particularly since 2000 with the advent of 4D-VAR at the ECMWF, the scores of the numerical weather systems actually has increased very regularly, and there's been a discrepancy that got very narrow after use of 4D-VAR and more observations from the northern hemisphere and southern hemisphere. And so this is how it progressed until now with at the ECMWF, actually. Now, if you account for the machine learning revolution and building of surrogates, those are typically what AIFS does, so the machine learning equivalent of the AIFS. So this is the gain that you actually get from using the surrogate model. Okay, so this is the, it used to be a silent resolution, and now there's been a big jump here. So this is the ML revolution, the AI revolution. Okay. However, there's still a debate, and this is discussed to some extent. And Remy mentioned data assimilation for the explanation, but actually I don't think it is the case. It's more like post-processing. I mean, why is it? Is there really something better that we learn on the dynamics when we use a surrogate model in data? In numerical weather forecast, or is it some statistical adaptation? And so this is something which is still debated. It's not completely clear yet. We've seen all the surrogate models from Michael's presentation this morning above the orange horizontal line, but actually it's just a few % above the line. And so it may be that actually this only comes from a statistical adaptation on top of the forecasting that is learned actually, which is learned by the surrogate model. And so this is, of course, everybody in the operational centers think about that, but then there may be ways to actually measure that and see how informative from the standpoint of physics is a forecast and what kind of statistical adaptation does the surrogate model carry out actually compared to the AFS, high resolution AFS. And that's kind of work that is ongoing at the SMWF, trying to see what's, where is the difference coming from, okay? But it means for us, at least in data assimilation, that we can't really give up on physical models. We really want to use those machine learning and emulators, but we still need to have the physics. And so one strategy could be actually try to combine them, and that's typically the strategy we see with the neural GCM, to have a hybrid model, keep a physical part, and add on top of that a neural network part to make some corrections. Okay, and this is something that I'd like to illustrate first. Okay, now I'm going to tell you how to use data assimilation actually to learn a surrogate model, but using sparse observations and noisy observations. So the way to do it in a very simplified way, but it's been explained in a much better way before, the way to carry out that program, if you have dense, regular, and regularly spaced, distributed, and perfect observations, is typically to use this machine learning cost function. This is just the least square estimator of the dynamics, of the parameters of the dynamics P, and using all these, this is typically error file that we're using here, and we want to minimize this cost function using the fact that the neural network is differentiable, and then we can estimate all those parameters, and hopefully get, a lot of work, and then estimate this nice surrogate model that we've got to move from time tk to time tk plus 1. Okay, but since we have sparse and noisy observations, there is no easy cost functions actually that looks like that we could use, because actually we don't have, if we assume that we can't use error 5, and now we are stuck because we absolutely need error 5, to go beyond that we really need to use all the observations that we actually have on the Earth system. And so we need to have a methods to actually help us learn from sparse and noisy observations. And again, it turns out that data assimilation is typically the way to carry out this program. And this is the inverse problem strategy to carry out this program. Data assimilation does that by construction, and this is what it's meant for. So hence the idea to use data assimilation for carry out the same program. Okay, and when you write the cost function, so using a Bayesian analysis, and you write the cost function in terms of all the variables that you want to deal with, which is the parameters of the neural network of the model that you want to learn, the surrogate model that you want to learn, but also the trajectory of the system. So this is the hidden variable that we now introduce because we want to connect them to the observations. You end up with this cost function with the discrepancy to the observation, and this is the discrepancy between due to the model from time tk minus 1 to time tk. And it turns out that this cost function is actually a very, very hyper-classical one in data assimilation. This is any students in data assimilation actually learn this cost function. This is typically the one of 40 var, and actually the weak constraint variant of 40 var. And this is typically what you have to minimize to carry out an analysis in data assimilation. But here the emphasis is usually it used to be just a few physical parameters that we learn from, but now we can actually learn all the weight and biases of the model. Okay, and so the program, instead of learning the simple machine learning cost function that we saw before, we have to minimize this cost function, which is, of course, more difficult than the previous one. But it turns out that if you go to the fully observed system with H, so the observation operator goes to the identity, and you've got no noise anymore in the observation, or almost no noise. So the mathematical limit actually of this cost function is the one that we saw before, the machine learning one. So it's consistent with what I've shown earlier. So we have to minimize this cost function to actually carry out this program and learn the model from a noisy and sparse observation, which is something that you can actually do. There are many ways to do that, but it's difficult because the parameters P are not really of the same nature as the hidden variable, the state variables. So from an optimization standpoint, it's quite different. And actually, a good strategy is to use a coordinate descent, meaning that you minimize on either the P parameters of the model, or you minimize on the trajectory, on the init state. Okay, and it's actually good because you can reuse some of the most classical methods, both in machine learning and in classical data assimilation. So to minimize this cost function, you would actually start with some values for the model, and then fix this model. So you would have a typical auto-differentiable model. And then you can carry out classical data assimilation method to minimize this cost function on the state trajectory. And you could pick any of your favorite data assimilation method, and then you fix the trajectory, and then so you get a new data set somehow you're on era 5. And then you use pure machine learning method to update the P, and then you can, via coordinate descent, you can actually update all those parameters altogether. And this leads to a way actually to learn the model from noisy and partial observations. Okay. Now, if you want to help the minimization and not start from a completely blunt model like persistence or something very difficult, and if you also think that physics is still very important, which I try to mention that before. I mean, you can use this an hybrid type of model, typically like we saw with neural GCM, but that's something also that we've done at ECMWF. And so you still have the physical model. So neural GCM, it was something that they wrote in Python and JAX for their core dynamics. Here, this is the IFS, because this is with the ECMWF in mind. And we want to add some physical corrections, neural network corrections. So this is the kind of neural network corrections that we add up on top of the IFS. And this is the hybrid model that we came up with. And it turns out that actually it can be embedded into this coordinate descent scheme, even though we will focus only on the first loop of this scheme. But the idea is the same. And the good thing is that we're going to be helped by the fact that we know the IFS, so that we only have to learn the correction on top of it. But as opposed to classical machine learning, we can learn the state, do classical data assimilation, and at the same time update the parameters of the surrogate of the machine learning model, correction on top of the IFS. Okay, and so the typical, you can do that offline over a big window, or you can do that online. So really, this like numerical world forecast with sequential updating. Every 6 hours you update your system. But now, instead of only updating the state of the system, the state of the atmosphere, you will update the correction that you have on the IFS, okay, through machine learning. And so a typical, very simple, because now we are thinking about implementing that on the IFS, or we were thinking about implementing it in the IFS, so really in the forecasting system. We need to make approximations so that it fits into the operational system. And so this is the typical cost function that we wrote, which is a simplified version of what I've shown earlier, where we have to learn not only the state of the system like a typical 4D var, and this is typical 4D var cost function, but also some parameters. Some parameters of the neural network correction. Okay, and that's typically, okay, so, and then we carry out the program that I've shown earlier. So it leads to a 4D var, but that has not only estimate the state, but also the parameters of the correction of the IFS, on top of the IFS. Okay, and so, but it needs some work because we really wanted to fit into the IFS framework, so you need to build your own, because it's written, IFS is written, even though we got the adjoint of a simplification of it, but it's still written in Fortran, so, and the whole system is written in Fortran, so you actually, the model is in Fortran, but actually, so you need to write some interface between whatever layer you want to implement of your neural network, but also the AFS, which is written in Fortran. So actually, Alban, who is in the room, actually wrote the own layers, and so as to have a rather simple way to set of neural networks to implement and that are actually implementable and be used can be used in the within the IFS system. Okay, and here this is the correction, which is a vertical correction, although it has some special, it can account for some of the special correlations. But this is a very simple vertical method, especially because all the physics that Thomas mentioned is usually, you know, it's really within the vertical, and all the microphysics also within the vertical. So that's where we first think about using this neural network correction on top of the IFS. And the nice thing is that, technically speaking, it has been built so that it actually only necessitates a few corrections within the IFS data assimilation system. So just a piece of code showing that there's only a few corrections of the overall scheme in the IFS system to actually fit the whole program in. And so from these vertical ideas, and then with some simplification, we are able to actually modify the code of the IFS so that it can actually work. Okay, and those are the first experiments that Alban and Marc actually did at the ECMWF, showing some improvement on the IFS forecasting system, and so those are the So on the right, those are improvements, and this is typically the case for pressure and temperature. No, I mean not as much for vorticity and divergence, but it also improved the humidity. And this is using both offline and then later on online. So, you know, numerical forecast is now not only forecasting the state of the atmosphere, but also improving constantly the model. Okay, and this is the typical scorecard that actually Remy showed is on. And this is the typical scorecard, and with a lot of blues, meaning that there is a lot of improvement from the method. Okay? Now I'm going to talk about another topic, which is, and I want to be careful about that because I'd like to really, so there are many ways to use machine learning into the data assimilation methods, or maybe to build some shortcuts for some of the pieces of data assimilation. So there are many ways, many things that you can actually do. Here, even though the goal will actually be to learn the analysis step, so the analysis step of data assimilation that I was mentioning, with AI. So instead of learning the model now, we suppose that we know the model, the forecasting model. Now we want to focus on this, that key data assimilation part, which is the analysis, okay? Bringing together the observations and the model forecast, and you know, get an estimator from them. Even though the goal initially was to actually learn that, and this is something that a lot of groups in the world have been working on over the past year, I'd say, no more than that. And you'll see a few papers popping up on that subject recently. Here, ultimately, it won't be about trying to be good, even though it is very good, on carrying on this analysis with only machine learning method. The goal now will turn out to be to actually learn something new on data assimilation from AI, from carrying out this program. Okay? So it's something that we didn't know about data assimilation, or we completely overlooked, and I can testify of that because I've been working on data assimilation for the past 20 years. Okay? And so, okay, so the goal, I mean, so this is mostly on toy models, so that's something we can actually easily test. So the idea is to carry out this analysis. And so this EF is the ensemble forecast. So this is really the forecast of the model, but this is an ensemble like you would do with the GenCast or the IFS ensemble. And this is this is what's called the innovation. This is just the difference between the observations and what the model actually predicts. So this is really the source of information that you get from the observations, and which is key in the analysis and improving and correcting the model. And this is the correction, so the incremental form that you build on top of the forecast. This is the correction that you make on the forecast. Here, this is an ensemble, as this is done in all the operational systems, like typically at the ECMWF or Météo France. And A stands for analysis, so this is the estimator, the outcome that you got from the analysis. Okay, and so this is the analysis part, and we want to learn actually this step. So that's why there is this theta, this is the set of, this could be P, this is the set of parameters that we learn. we want to learn, and A theta will be a neural network. Okay? And then we want to make a forecast, and of course, this is the second step of data assimilation sequential scheme. But here we were going to assume that we know the model. I mean, we could actually learn it all together, but this is not really the point of the here. So I assume that I know, but it has to be auto-differentiable because we want to go back propagate through it at some point. Okay, and I'm using a very simple, this is on a lower model, so a very simple neural network. The only important thing is that it's actually based on the convolutional neural network, and because I'm going to use transnationally invariant dynamical chaotic system, the fact that it's a convolutional neural network is a great help here. But this is the only technical important point. Okay, and what we want to learn is actually through this supervised cost function, where we want to carry out, roll out, several steps of the data assimilations. And we want to, at each step, we want to compare the truth. We assume that we know the truth, so the state, what is really the state of the atmosphere. And we want to compare it with our estimator, which is the analysis. Okay, but we do carry out, we carry out this data assimilation experiment, and each time step, we actually compare it with the truth. And because there is this sequential dependence in time, you need to backpropagate through several steps, time steps actually, and this is very important to actually learn something very clever on data assimilation. Otherwise, you wouldn't be able to do that. So so it seems like a very simple cost function, comparing the truth with the estimator, but actually, technically, it's quite involved because you need to backpropagate through several time steps and through a data assimilation procedure. Okay. Even though it's supervised learning here, it turns out that it also works with unsupervised cost function. That's something that I've tested also, and it works as well. It's, of course, more difficult to optimize, but still it works. And the first thing that we actually learned about this is the fact that first it does, when you learn this analysis, it turns out that this is the level of accuracy that you end up with as a data assimilation method is as accurate as the best method, almost the best method known for this type of toy model. And this model is called the Lorentz 96 model. This is the typical chaotic model, which is a very simple illustration of the atmosphere, of the chaotic atmosphere. So it's the accuracy that you get is actually very good and much better than any statistical method that you could get. Very simple statistical method that you could get. So it does better than, for instance, 3dvar or 4dvar, and it does as well as the ensemble Kalman filter, which is supposed to be the best method in this context. So that's a good thing because you already get something which is as good as almost the best method in the system. But the most striking thing was actually to realize that actually it does not depend on the ensemble size. And this is where it completely destroys all our belief in data assimilation over the past 20 years. Because we all thought that, at least within the context, it is very important to have this ensemble, okay, and a significant number of members of the ensembles to have a good estimate of the uncertainty on the estimate of the system. Okay, so you need to have UQ to actually to make a good data assimilation system, an accurate one. And it turns out that it tells you that it's essentially the system is essentially insensitive to the ensemble size, which is striking because this is really not what we thought we would obtain. Okay, second thing is that it's super stable. And it's known in data assimilation that actually it's not, I mean, when you use an ENKF, you need to have some tricks that we understand why, but you need some tricks like inflation, localizations, that are required to have a stable data assimilation experiment and methods. And here you don't need them, which is a very big surprise. And you can actually show, at least numerically, empirically, that actually it does, this is typically, with 3dvar or 4dvar, you would never get this score. So this is the root mean square error for comparing the analysis to the truth. And with any other method, you would actually obtain something much higher, twice higher, actually. Okay, and you can actually show that the fact that this is a nonlinear neural network is key. So this is not just a linear adaptation, clever one that we never thought about. It's the fact nonlinearity is key, and beyond that, you need this dependence on the forecast state, actually, an ensemble, but now a state is enough. And this dependence is quite intriguing. So it means that actually the system the neural network system analysis is actually learning something not only from the observations, okay, but it's learning actually something from the forecast state. It doesn't need the ensemble, it's just the forecast state. It looks something into, look up something into the forecast state, and it learns something about the uncertainty of the system, of the data assimilation system, which is something that we never really thought about in the data assimilation community so far. Okay, so one way to try to understand what's happening, because this was a bit puzzling, is try to make some expansion of this, so the neural network incremental analysis. And in terms of classical objects that we are used to deal with in data assimilation or in estimation theory in general. And this is expanding in terms of the innovation, so typically the observations, so that we should actually get the Kalman gain. Okay? But now we know that it actually depends on the states, which is not something that we were expecting. So it does depend on the states. And so if we make this expansion and we check that actually, yeah, it is a valid expansion, we can try to estimate numerically K so as to get an idea of what is this Kalman gain that actually the system estimates. Okay, and that's something that you can learn using numerics. And you can not only can you estimate the Kalman gain, but you can also estimate the key object in data assimilation, which is the analysis error covariance matrix, which encodes all the errors, all the covariances, the error covariances that you've got on the analysis, on your estimate, on the main product of data assimilation. So this is the second main product of data assimilation, which is the analysis error covariance matrix. And that's something that you can extract numerically from this operator, from this neural network operator. Okay, and you can compare it with an ensemble Kalman filter that you run concurrently. And what is really nice is actually it really is very close. The two error covariance matrices are very close, and their main modes are actually very similar. In terms of magnitude, they are actually very close to each other, and even in terms of of vector space, they are extremely close. So they are actually learning the same instabilities in the state space. They are learning something very, very similar. So actually, what we learn here is that this neural network operator for the assimilation, for the analysis, is actually learning something very similar with only one single forecast. It learning the same as what the NKF can do with an ensemble, or need to do with an ensemble. But on top of that, it applies by itself some multiplicative inflation so that the system is actually very robust. Okay, so one of the things that we learned from this is actually the fact that so now we learn that this operator, actually neural network operator, extracts something from the forecast states itself. It doesn't require the ensemble. It learns something from the forecast states. We also learned, because we compared that to the ENKF that we have a good understanding of. So we know that he learned something about the dynamical features, not only of the forecasting model, but of the whole data assimilation system as seen as a dynamical system per se. Okay, so it learns a lot of things about all the what's happening within the sequential data assimilation schemes, and it can extract some of this information only from one single state. Okay, and so on the dynamical system theoretical side, it really looks like there is some kind of the Osselelec theorem. I'm sure some of you, if you know about Lyapunov vectors and Lyapunov exponents, you heard already of the Osselelec theorem, which is the multiplicative ergodic theorem. And it looks like there is also a multiplicative ergodic theorem that actually applies not only to the dynamics here of the system, the underlying dynamics, the forecasting system, but to the whole sequential data assimilation system seen as an ergodic dynamics. And this might be the reason why actually the whole thing works. Okay. There's also, to conclude on the topic, there's also a few things that are nice, and the fact that we actually understood that those, whatever it learns from the states, they must be local objects. So they are not actually, they are really decomposing the state and learning some of the local features within the state, especially if you start to increase the size of the system, which you can do with this low order system, but you keep the size of the neural network fixed. you still learn a very good method, something which is as good as the ensemble-Kalman filter, the best ensemble-Kalman filter that you can build within the system. Okay, it means that whatever it learned actually on this small dimensional size in the system, it's useful and it's fully useful for a much bigger size for the when you increase the size of the system. Okay, so it really it must have learned something local, some local features within the state that can be spotted on the higher dimensional extension of the same model. And it even turns out that that actually you can use the Etheta, because it's a convolutional network, you can actually use this the neural network that you learned on the small dimension system. You can actually use it out of the box on the much higher dimensional model, but still the same types of dynamics. Of course, this is the same model, but just with a number of grid cells, a much bigger number of grid cells, and it turns out that it works as well. So whatever they learned, embedded within this convolutional network, actually it is still there, and it spots whatever it has to spot on the higher dimensional systems. Okay, so that's kind of nice, but it proves that those are local features that are extracted. Okay, and this is now you can try to play the game of okay, I want to see what those features look like, and this is the so using some of the invariance of the system. It's because you need to look at some further order sensitivity, so it starts to be a big tensor object. Even though it's a low order model, it starts to be quite complicated to extract. But still, you can, I mean, this is the typical incremental Kalman gain, the average typical incremental Kalman gain that you would get when you excite the set of the system at the center of the domain. And you've got this object. And this is really those local patterns that are really seen and spotted in the state and are helpful to make this the proper carry out the analysis by the neural network. Okay, so I want this. Yeah, this has been. We also tested that on higher dimensional system, and there are connection with dynamical system theory, and there's something really that we completely missed in data assimilation so far. Now, of course, it remains to be seen whether it can be applied on a much higher dimensional system and especially heterogeneous system, and that we don't know yet. Okay, and then maybe I'd like to take the opportunity, I mean, to conclude that we are actually hiring at École des Ponts, we are hiring a long-term postdoc, typically on this topic on generative AI applied for numerical weather forecast and possibly data assimilation. And I mean, the goal is really to understand and learn what's actually happening within those neural networks that accomplish that kind of marvels actually for data assimilation or for generating an ensemble. Thank you.